In 2.2, we have more properties of matrices that we're going to look at. The first properties deal with basically addition and then scalar multiplication. And they're kind of the same as what you would think. If we add matrices together, the order doesn't matter. Because if you think about, we're just adding corresponding components. So if we're adding numbers together, a regular real number addition is commutative. So if we're adding matrices where we're adding corresponding components together, that's still commutative. It's also associative. If we are adding three matrices together, it doesn't matter which order we add those together in. We can add the last two and then add the first one, or add the first two and then add the last one. If we have two different scalars that we're multiplying together times a matrix, we can either multiply those two scalars together first, or we can multiply one of them times the matrix, then multiply times the other. The identity is true if you multiply by the scalar 1, multiply every component by 1, you get itself for every component. So you get this. Also, if we have a scalar times the sum of two matrices, we can basically distribute by a scalar. We can do that scalar times the first, that scalar times the second, and add them together. Or if we have two scalars that are added together times a matrix, we can do the first scalar times our matrix, the second scalar times our matrix, and add those together. So as far as addition is concerned and multiplying by a scalar, addition or association, commutative, distribution, all of those are the same. Where we get a little bit different, though, is where we run into multiplying matrices together. Not everything is different about multiplying matrices together, but some of it is. So if we take one matrix times the product of matrices, that is associative. We can change the order we multiply those together. We can multiply the last two and then do that times the first one. The first two then times the last one, that's okay. We can distribute a matrix. Keep in mind, this is true as long as the sizes match. As long as the number of rows and columns are such that these operations are possible. So that plus that still holds true, as you would think. We can add two matrices together times another one out front. Notice the difference between this one. Let's see. The difference between these two, the two that are added together are on the right side here, they're on the left side here. But we can still distribute, and we still get what you would expect. Not always the case with every property. It's not the same as with regular real numbers, but it is here. We have a scalar times the product of two matrices. That's equivalent of taking that scalar times one of those matrices and then multiplying it times the other one, or taking that scalar times the second matrix and then multiplying that times the first one. So all of these things, all of these are things that hold true. So sometimes it might be easier to multiply things in certain orders. We just have to keep in mind all of these have to deal with association or distribution. But notice there was no commutative law for multiplying matrices together. So we didn't have one that said A times B and B times A are the same. That's in general not going to be the case. Again, association and distribution work, but not commutation or commuting. So let's see. We've done some matrix, we've multiplied some matrices by some identities. The next thing in general that is mentioned is theorem 2.5. This is still in section 2.2, but it talks about solutions to systems of equations. In class today, we talked about solutions for homogeneous systems of equations, and we talked about some properties of those, but these are systems of linear equations in general. So exactly one of these following statements is true. And I guess I should say exactly one. The system has one solution, or the system has an infinite number of solutions, or the system has no solution. So no great brain teaser there. We're going to get one of three things. We're either going to get one solution, we're going to get infinite solutions, or no solution for linear systems. Key word here is these are linear. Think about it. If we have two lines that intersect, we get one solution. If we were to have two planes that intersect, those intersect at a line, so there are infinite solutions. But if we intersect that with another plane, then all of those intersect at one point. So we're not going to have a possibility of having two solutions, three solutions, four solutions. We either have one, none, or infinite. All right. Next term we introduce is a transpose. So if we have a matrix A, to denote the transpose of that matrix, we put the superscript T on that matrix. And all that means is to swap the rows and columns. So whatever is the first row in this matrix, if we transpose it, that becomes the first column in the other matrix. The second row of this matrix becomes the second column of the other matrix. You can do that with larger matrices. Let's do 1, 0, 2, 1, 3, 0. If we transpose that, the first row becomes the first column. The second row becomes the second column. Now notice if we take that answer and transpose it, then the first row becomes the first column, the second row becomes the second column, the third row becomes the third column, which gets us back to where we started. So if we have a matrix, if we transpose it, then take that and transpose it again, that gets us back to where we started. So we just basically rotated it all the way around. So there are some properties of transposition. That's the first one. If we transpose a single matrix twice, we get what we started with. If we have matrices that are added together and we want to transpose the result, we can transpose them separately and then add them if necessary. If we have a scalar times a matrix and we want to transpose that, we can transpose first and then multiply by the scalar. And probably one of the more useful ones here, the one that's not overly obvious, is if we have a product of matrices that's transposed, that's the second one transposed followed by the first one transposed. So notice the order does change if we have a product. If we do the product, then transpose it, as compared to transposing, then taking the product. So that order does change. And that has to do somewhat with the size and shapes of those matrices. So for homework, there are going to be some exercises where you're given a problem and you're asked, find the transpose of this matrix, or take this matrix, transpose it, and then multiply it times another matrix. So let's look at taking this matrix, let's call that A, and let's do A transpose times A, if possible. So the transpose of A, first row becomes first column, second row becomes second column. Let's see, can we do that times A? I think so, because, and let's think about that, that should always be the case. If A is m by n, then A transpose, we would swap the number of rows, swap the number of columns. Those will always match if we swap those. So we should end up with an m by m, in this case, a 2 by 2 matrix. Or, let's see, this is 2. Oh, we're doing the transpose first. So we're doing 3 by 2 times, I was looking at this one, times 2 by 3. We're going to end up with a 3 by 3. So this one times this one times that one, this one times that one, this one times the first, this one times that one, this one times that one, and then this one times the first, this one times the second one, this one times the last one. Now if we do it in the other order, we don't even get the same size matrix. So this one times that one, that's 16, 4, so 29. So that's row 1, column 1. Row 1, column 2, that's 4 minus 2, so 2, 6 is 8. Row 2, column 1, that's 4 minus 2, so 2, 6 is 8. Here and here, that's 1 plus 1, so 2, 4, 2 plus 4 is 6. So A transpose A times A transpose. So that just reminds us, how do we multiply vectors or matrices? How do we transpose? If we want the transpose of this, we let the first row become the first column, second row, second column. If this is row, 3 rows, 2 columns, 2 rows, 3 columns, since those match, we get a 3 by 3. Here we have 2 rows, 3 columns, times 3 rows, 2 columns. So since those match, we get a 2 by 2. So again, we shouldn't expect those to be the same, because the dimension of those two matrices won't even be the same. So a lot of the problems in section 2 are just dealing with what are the properties of adding matrices together, multiplying matrices together, taking a transpose, and so forth. As we get into 2.3, 2.3 deals with inverses of a matrix. So when we talk about multiplication, if I have the number 3, if I want the inverse of that, the multiplicative inverse, I'm looking for what number times 3 gives me the multiplicative identity. In other words, 3 times what would give me 1? Well, 3 times 1/3 is what gives us 1. So you may recall that the multiplicative identity, as far as real numbers, is just its reciprocal. So if I have 4/3, the number that I multiply that to get 1 is its reciprocal, 3/4. And when we talk about the inverse of a matrix, we're looking for a matrix such that when we multiply it times our original matrix, gives us the identity. Or likewise, if we multiply those in the opposite order, we also get the identity. So one thing that'll come up is only square matrices have inverses. Because in order for A times B and B times A to be the same and both give us the identity, for this product and that product to be the same, they have to result in the same dimension. And the only way those result in the same dimension, if I take an m by n times an n by m, and I end up with an m by m, and then if I swap that order, I do n times m or n by n times m by n. I multiply those together and I get n by n. The only way those are the same size is if m and n are equal, which means you have the same number of rows and columns. Same number of rows and columns makes it a square matrix. So that's one of the first things about inverse matrices, is that the only types that have these are square matrices. Now some matrices, even some square matrices, don't have an inverse, and those are said to be non-invertible. So let's see. Let's take two matrices and let's show that they are inverses of each other. So let's take that matrix A and this matrix B, and let's demonstrate that those are inverses. So let's do A times B. So we're going to take row times column, so -1 plus 2 is 1. Row and column, 2 minus 2 is 0. Row and column, minus 1 plus 1 is 0. Row 2, column 2 will give us this entry, so 2 minus 1 is 1, and that's an identity matrix. It's a 2 by 2 identity matrix. If we were to check in the other manner, we'll do B times A. I'm going to take this matrix. The first one. If we can multiply together in that order and get the identity matrix, then yes, these two matrices are inverses. So this one times the first, so row times column gives us the row 1, column 1 entry. So 1 times -1, -2 times -1, so we get a 1. Row 1, column 2, so 1 times 2, negative plus -2 times 1, so 0. Then row 2, column 1, 1 times -1, -1 times -1, so 0. 1 times 2 plus -1 times 1, so 1. So yeah, that's still the same size identity matrix. So these two matrices are inverses of each other. So different ways to find inverses. So if I have some matrix, let's see, let me find one that'll to do. If I have a matrix 1, 2, 3, 7, I want to find some matrix so that when I multiply times that, I get the identity. So let's call this A, then this would be A inverse. So I'm wanting to find some matrix let's see, what notation do they use? We can call this row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So when we multiply all that together, we get this. So we do this times that, so plus this times that, so row 1, column 1. That yields the first position, which has to give us 1. We take row 1 times column 2, 1 times x1, 2, 2 times x2, 2. That gives us this component. Row 2, column 1. This one times that one. So row 2 times column 1, 2, 1, that gives us 0. Row 2 times column 2, so 3, x sub 1, 2, 7, x sub 2, 2. So we do row 2, column 2, that's row 2, column 2, that gives us 1. So notice that basically gives us 4 equations, 4 unknowns. So if we group these together, we've got, notice these two have the same variables in them, with the same unknowns. And then these two have the same unknowns. So notice this and this, those are the same system of equations with just different resultant vectors. So instead of solving the systems of equations separately, let's just solve this as one system. Let's put our coefficients on the left, and then on the right, put our resultant. So for one answer, we have 1, 0, 0. For the other one, 0, 1, 1. So essentially, without getting lost in all these details, if we have a square matrix, we can put it on the left. We can put an identity matrix of the corresponding size on the right of an augmented matrix. We can reduce this to reduced row echelon form, and if we can get an identity on the left, then what we have on the right will be the inverse of our original vector. It'll be the solutions of those, x1, 1, x row 1, column 2, so forth. I think I labeled those backwards, but you get the idea. So let's do that. So let's take our matrix here, and let's row reduce it. So we have a 1 here, we need a 0 here, so we'll take -3 times the first row, add it to the second row. That'll give us our new second row. Our first row we're leaving. Our second row, so -3 times this is -3 plus that is 0. -3 times that is -6 plus 7 is 1. -3 times this, that's -3 plus 0. -3 times this is 0 plus 1 is 1. So now that's row echelon. Now we need to put it in reduced row echelon so that we have an identity on the left. So we need a 0 there. So to get a 0 here, we need to take that row minus 2 times row 2. Notice if we do -2 times this, that'll make -2 so that that will cancel out. So the bottom row is staying. So if we do the first row, then twice this one, 1 minus 0 is 1. 2 minus 2 times that is 0. 1, -2 times this is 6. 1, 6 is 7. This one minus twice this one, that's -2. So 0 minus 2 is -2. So our inverse is 7, -2, -3, 1. So our original vector was this. Let's see. That was our original vector, that was our new one. So let's verify that those are inverses by multiplying them together. If we multiply those together and get the identity matrix, then they are inverses. So row times column, that's 7 minus 6. Row times column, that's -2, +2. Row times column, that's 21 minus 21. Row times column, that's -6 plus 7. So yes, that is indeed the inverse. Now, they'll go on to show that for a 2 by 2 matrix, there is a shortcut to finding an inverse. If we have a matrix, let's take that same one, 3, 7. That's matrix A. Then for a 2 by 2, we can do 1 over the determinant of that matrix, which the determinant of that matrix comes by doing the row 1, column 1 times row 2, column 2 component minus row 2, column 1 times row 1, column 2. So that's the determinant of A. We'll talk about determinants later. And we're going to do that times a matrix where we swap these diagonal components. We swap these diagonal components and take the opposite sign. So we move this 3 up to here and change the sign. Move this 2 down here and change the sign. So in general, if our vector is A, B, C, D, then the inverse of that can come from doing 1 over A times D minus C times B. That's our scalar times the matrix. Swap A and D, swap C and B, and change the signs. I'm sorry. Now that I go back and look, we don't swap these. They stay in the same place. We just change the signs. So minus C minus B. So these shouldn't be swapped, just the signs changed. So the diagonal from left to right going down swaps. The diagonal going up from left to right just changes the signs. So let's see if that works. Let's see if we get that same thing. So 1 times 7 is 7. 3 times 2 is 6. We swapped 1 and 7. We changed the signs of these. We have a 1 on bottom, 1 on top, so 1 times that matrix gives us 7, negative 2, negative 3, 1, which is the same thing we got there for our inverse. A bit shorter. Again, that's kind of a trick for 2x2s. It doesn't work with all of them. But if we want to find the inverse of a 3x3, for example, if we have this matrix, if we want to find its inverse, put it in augmented matrix form with a 3x3 identity matrix. Row reduce this until you have an identity on the left, which basically means you're in reduced row echelon. And then whatever you have on the right, if we called that A, then this will be A inverse. So just a couple properties of these before I turn you loose to work on some problems. If we have an inverse and then invert that, that gets us back to our original matrix. If we have a product of matrices that we want the inverse of, similar to the composition, or I'm sorry, the transposition, if we apply the exponent, quote unquote, then it changes the orders. So we would do the inverse of B, the inverse of A, we would swap their orders and then multiply those together. So one thing that we will want to do is use these inverses for some particular purpose. And one of the most common purposes of inverses is to solve a system of equations. So let's remind ourselves of something we mentioned earlier. If we have two matrices that are equal, and I multiply a matrix on the left by a new matrix, if I multiply this on the right, then I have to multiply on the right on the other side. If I have two matrices that are equal, if I multiply on the left side, I have to multiply out front also on the right side. So if I'm out front here, I'm out front here. If I'm on the end here, I'm on the end here. One thing we mentioned is that when we multiply a matrix times itself, we get an identity matrix. And anytime we multiply an identity matrix times a new matrix, it gives us itself. Well, that becomes useful. If I have a matrix equation, basically a system of equations, if I want to find out x, which x is our variable vector, A is our coefficient vector, B is our resultant vector. If I want to find our solution vector, then I can multiply out front by the inverse of A on both sides. So multiplying A inverse times A, that gives us the identity. Identity times the x vector is itself. Anytime you multiply something by identity, you get itself. So this gives us a form or a way of solving a system of equations. So let's use that in order to solve a system. Let's take this one. Which this one would be easy to solve just using old-fashioned elimination. But let's use our matrices. Our coefficient matrix here is 1, 2, 1, negative 2. Our x vector is x1, x2. Our resultant vector, negative 1, 3. Notice if we multiply the left side, when we do row times column, we have 1x1 plus 2x2 for our top entry. 1x1, 2x2, that equals the top entry on the right. On the bottom, row times column, that's 1x1 minus 2x2. That gives us our row 2, column 1 entry. On the left, our bottom entry on the right. So this is A, X, B. Remember from vectors, we normally put a bar over the top to refer to something as a vector. So to get X, we want to multiply out front over here by A inverse, and out front over here by A inverse. So let's get A inverse. Since this is a 2 by 2, we can take the determinant, 1 times negative 2, minus 1 times 2, times, swap along this diagonal, change the signs along this diagonal, so we're going to take 1 over negative 4 times this matrix. So that's a scalar times a matrix, so negative 1/4 times negative 2. Negative times negative is positive. Negative times negative is positive. Negative times negative is positive. Negative times positive is negative. Now, quick little side note. If the determinant of this vector were to be 0, that means there's not, that would make that 0 on bottom, which would make this undefined, which means there's no inverse for A. So a 2 by 2 is invertible only if the determinant is not 0. Again, that's not necessarily something you have to know now, but in the future we'll discuss. So let's go back. If we want to get X by itself, we're going to multiply out front on both sides by A inverse. So those make identity. So that'll leave us X on the left. So we're going to take 1/2, 1/2, 1/4, negative 1/4, and multiply that by our resultant vector, negative 1, 3. So our answer, when we do row times column, we get 1/2 times negative 1, so negative 1/2. First row times that column, so 1/2 times 3, so that's plus 3/2. Then the second row, first column, gives us down here, so 1/4 times negative 1 plus negative 1/4 times 3. So minus 1/2 plus 3/2, same denominator, so that's 2/2 or 1. Minus 1 minus 3, so minus 4/4 or minus 1. So the resultant of this system of equations is 1, negative 1. That's the solution of this system of equations. I said the resultant, but that's the solution of this system of equations. Notice 1 plus negative 2 is negative 1. 1, negative 2 times negative 1, so 1 plus 2 is 3. So yeah. So for any of these, if we want to solve a system of equations, if A is invertible, then multiply out front on both sides by the inverse of A. So out front on both sides by the inverse of A. So A inverse times B will give us the solution set for that particular system of equations. So that's what 2.3 deals with.